In chapter 3, we learned how to take all sorts of different derivatives. And now in chapter 4, we're going to learn a whole bunch of things that we can do with those derivatives and some different things that they tell us. Our first few sections of chapter 4 all have to do with different characteristics of graphs. So some different things the derivative can tell us about a graph without us even looking at the graph. So we know back from chapter 3 that the derivative can tell us the slope of a tangent line. But if we actually look at the patterns of the slopes, we can figure out even more about this graph, the graph of this function that we're analyzing. So 4.1, we're going to talk about maxima and minima, and there's a couple different types of maxima and minima, and we'll talk about what those are and where we can find them. And this whole first few sections of chapter 4 really are related to characteristics of the graph. So we're going to keep seeing maxima and minima come back here in these next few sections. So this is really just a little introduction to it. And I don't personally like the really formal technical definitions that are provided in the textbook. They're very hard to read. They're kind of confusing. So I'm just going to introduce a much more informal, I think, plain English definition here for maxima and minima. But you can always look up those formal definitions if you like. So you probably have a little bit of experience already with maxima and minima from algebra class. We start talking about maxima and minimas when we are analyzing graphs of quadratic functions, because we do application problems and we say that the max and the min always occur at the vertex of a quadratic. So this is the same maxima and minima that we talked about back with quadratics in algebra. But back then, we didn't use calculus to find it. We used other ways to find it. But it's the same idea. The maxima is the highest point on the graph. And I actually don't want to say point, because here in calculus, we tried to start the trend back in algebra. The maxima actually only refers to the y value. So it is the highest value on the graph. And the minima is the lowest value on the graph. And we can be looking at the entire graph, or we could just be looking at a piece of the graph. And that could potentially give us different answers. So we would have to specify that at the beginning of a problem. So the technical definitions include less than and greater than symbols, and talking about being in a certain set, not a certain interval, and things like that. But really all it boils down to is we've got a maxima if it's the biggest and a minima if it's the smallest, or maxima if it's the highest, minima if it's the lowest. And one thing I do want to point out here is that there could be more than one maxima. There could be several spots on the graph where the graph goes up and reaches that highest point multiple times. So the highest value could be reached multiple times. And then the same thing for the minima. If you think about the sine and the cosine graph that just continuously go up and down and up and down and up and down and keep hitting those same high values and low values, those would have multiple maximas and minimas because they keep going up and hitting the same exact y values over and over and over again, the same highest and lowest y values over and over again. So there isn't necessarily just one highest point and one lowest point on the graph. There could be multiple. There also are two types of maxima and minima. So we could have two different points labeled as maxima because they're two different types of maxima. So I want to demonstrate this with a graph and just show you the different types of maxima and minima and how they could be at different spots or they could be at the same spots. So let me draw a graph here. All right, not messing with it anymore. Okay, so we're going to start off with the absolute highest point on the graph. And that is at 9, 4. There is no other point that goes higher than that. There's no other point on this graph that has a y value that's bigger than 4. Now, it would be perfectly fine if there was another one that had a y value of 4, because we said we could have that maxima achieved at multiple places. That would be perfectly fine. What we're concerned with is that nothing goes higher than that, and it doesn't. So because this is the absolute highest point on the graph, it's called the absolute maxima. And that is because there is nothing higher anywhere. And that is at 9, 4. Now, the absolute minima is kind of tricky. So all we would have to do is flip that around and say, what is the lowest point on the graph? So if you were to write out all the points on this graph and look at the y values, we want to know which point on this graph has the smallest y value. And it's a little bit tricky. We do have a point over here at 5, -4, but technically, all the way on the right-hand side, we've got an arrow, which means after about 17, this graph just continues to go down forever. That means there is no absolute minimum because the graph goes down forever. If you had to try to guess at how low this graph goes, I could always come up with a lower point because that arrow means it never stops going down. So that's because that blue arrow there pointing down. So we have some other types of maxima and minima, and those are relative maxima, minima. And that's not when we're looking at the entire graph, but we're just looking, or we're just zooming in to one little area. And those are our hills and our valleys. So if we were just to zoom in at this little area right here, we would have a lowest point in that box. Now, it's not the lowest point on the entire graph, but it is the lowest point in that area. So on an interval from about 3 to 7, between 3 and 7, there is a lowest point. And it's always going to make a valley. That is called a relative minima. And it's the lowest point in that area. And there's actually another relative minima on this graph. And it doesn't have to be lower than the one we just found. The only criteria is that if we draw a little box around it, it will be the lowest one in its own little area. So approximately at 12.2, so my point there is a bit off. At approximately 12.2 here, there's another lowest point. So if we just looked on the interval from 10 to 14, 12.2 would be the lowest point on the graph. So there's a second relative minima. There's one here, and there's one here. Because either one of those little areas, if we zoomed in, we would have a valley. We would have a lowest point on the graph. So if we, again, flip that same idea around and we try to zoom in and find a highest point on the graph, that would be a relative maxima. And those are the tops of our mountains. So if you see any mountains on the graph, those are going to be our relative maxima. So it looks like we have one right here. Now we've already called this point the absolute maxima. So it is possible that one point can be both absolute maxima and relative maxima, or absolute minima and relative minima. But if we were to zoom in a little area around 9.4, it would be the highest point in that area. So that point is also a relative maxima. It is the highest point in that area. And again, we said that our relative maxima look like the top of a hill or a top of a mountain. There is another place on this graph where it looks like we've got the top of a little hill. And if we could just zoom into that area, we would have a highest point. And that's over here. If I could just zoom in right here, I would have the top of a mountain here at 14.3. And I'm going to do it in orange, just like I did my other one. If we could zoom in at 14.3, we would have the top of a mountain. And in that box around 14.3, 14.3 is the highest point in that box. So just in that little relative area, 14.3 is the maximum. So absolute maxima and minima are usually relating to the whole entire graph. Or if it's just on an interval, we want just the one highest point and the one lowest point. But relative minima, we can have lots of them, and they can be higher or lower than each other. We're just interested in how they compare to their surroundings. So for a relative maxima, in order for something to qualify to be a relative maxima or minima, they just have to be higher or lower than their neighbors. If they're the highest or the lowest compared to their neighbors, then they would qualify as a relative maxima or minima, even if they're not the highest or lowest on the whole entire graph. So let me write this out to some notes, because that was kind of a messy graph. We've got absolute maxima and minima. And these are the highest and lowest points on a graph. The absolute highest and lowest. And then we have relative maxima and minima. And these are also highest and lowest points, but they don't have to be on the whole entire graph. We're only comparing them to their immediate surroundings. So they are the highest and the lowest points in their area. And there's actually something calculus related that's really unique about those points where we have relative maxima and minima that we will talk about in just a little bit. So it never came up in this graph because I didn't plan it out correctly, but that hole at the end over here could possibly make a difference. So let me show you a different example, and I'm going to try to keep this video about 30 minutes. But this has more to do with finding absolute extrema on a closed interval. In a later section, we'll talk more about what's happening over the graph of an entire function. But really in this section, we're just going to talk about what's happening on specific closed interval. So there is a theorem that guarantees us that if we are working with a continuous function on a closed interval, then we will always have an absolute maximum and an absolute minimum. So continuous functions. In continuous functions, the fastest way to figure out if you have a continuous function is if you can draw the entire thing from start to finish without ever lifting your pencil. So continuous functions on closed intervals, that means both of your endpoints are filled in and you can use them. Will always have an absolute maximum and an absolute minimum. Well, the example we just looked at earlier, the graph I just showed you, we didn't have an absolute minimum, and I'm going to go back up to that graph in just a second and show you why. So if we look back up here, the interval that we're working with is not closed. This graph starts at 1 with an open circle. So the domain here that this graph is working with, this graph starts at 1 with an open circle, and the arrow on the right-hand side means it goes to infinity. So this graph is on an open interval. So we're not guaranteed to have an absolute maximum and an absolute minimum. So we didn't actually have an absolute minimum on this one. But if it's a closed interval, if we have a definite starting and ending point, then it is guaranteed that we will have an absolute maximum and an absolute minimum. And there's only 2 places that we need to look for it. They're either going to occur at the endpoints of our interval, or on the interior, somewhere within our interval, at a critical value. And we will talk about what a critical value is. Critical values are going to be really important here for the next couple of sections. So there's really only 2 things that we need to check. The endpoints of the interval are going to be given to us. We just need to figure out what those critical values are, and then we can check them and figure out what our answer is. So we're going to take a moment to talk about critical values, and then we'll look at a couple problems where we find absolute extrema on a closed interval, and then we are probably going to wrap this video up because I don't want it to be too long. So critical values these are places where your function either has a derivative equal to 0 or undefined. And that would probably look a little bit nicer written as a list rather than a definition. So for the function f of x, x is a critical value if either one of the following is true. Let me not use x. X equals a. So what our English definition just said is either f prime of a equals 0. So it's either where the function has a derivative equal to 0, or it's where the function is undefined. So f prime of a is undefined. So we're not going to have a's to check. We need to solve for the a's. So we'll know the function. We now know how to find the derivative for almost every type of function. And then we want to know where that derivative is either equal to 0 or undefined. So at that point, we'll just have like an algebra or trig equation to solve for those a values, which are our critical values. So let me first show you a graph, and then we will look at an example where all we have is the function. And all these graphs are going to be a little bit different, just so I can show you why we're guaranteed to have this maxima and minima, and where exactly our critical value is. All right, so a couple different graphs. They've got some different things going on with the endpoints. This first one is on a closed interval because both endpoints are being used. Both endpoints are colored in. Both endpoints are part of the interval. So this is a closed interval. The second one is an open interval because both endpoints have open circles at the end. We cannot actually use those end values. What exactly we call this one, it's some people call it open because one side is open, and some people call it half open. either way, it is definitely not closed. It's only a closed interval if both sides are closed. But it would either be open or half open interval. So our first one is guaranteed to have an absolute maximum and absolute minimum. But our other two are not. So let's look here. On the first one, the absolute maximum is at the highest point on the graph. Now the highest point is at an end point. And if we weren't allowed to use the endpoints, then we wouldn't have a max. So that's why we have to be allowed to use those endpoints. It has to be a closed interval. Now our minimum, this kind of looks like a piece of a parabola. The minimum looks like it's at the vertex, which I kind of meant to be here at the origin. Now, what is special about this point is if you try to draw the tangent line there, the tangent line is horizontal. Horizontal lines have a slope of 0. That is a critical value. That's a place where our first derivative equals 0. So our absolute max is at the end point of the interval, and our absolute min is at a critical value. And that's exactly the two places where we were guaranteed that our absolute extrema will occur. They will occur at either the endpoints of the interval or on the interior at a critical value. So on this second one, if we look for the max, if there is an absolute highest point, we do have an absolute highest point, even though it's an open interval. Now, it doesn't say we can't have them. It just doesn't guarantee we will. So we do have a max here, and the reason we have a max is because it's not at an endpoint, it is at a critical value. That is a place where we have a horizontal tangent line. However, we do not have a min, because if you try to locate the lowest point on this graph, it looks like it should be here, but because that's an open circle, we're not allowed to use it. So we wouldn't try to get the next closest point, because if you were to try to tell me what the next closest point would be to this endpoint, I could always split the difference in between and tell you a point closer. So technically, it's not possible to come up with the point that is immediately preceding this point and use that as our min. So we just say there is no min. Based on the way the graph is drawn, it looks like it should be here, but it's an open circle, which means we can't use it. On our last graph, if we look for the max, we look where the highest point is. It looks like this is the highest point somebody tried to draw, but again, it's an open circle. We can't use it. So there's no absolute max. And then if we try to look for the lowest point on the graph, we do have one. And the reason we have one, even though it's not a closed interval, is because it's occurring at a critical value, a place where we have a horizontal tangent line. So we could still have absolute maxes and mins on the interior of our interval. They're going to occur at critical values. If it's not a closed interval, then we can't necessarily use those endpoints, and sometimes our maxes and mins occur at the endpoints. So that's why we need to be able to use them. So we're going to look at an example really quick where we have a function, and then I will wrap this video up so it does not start to get too crazy long. We are going to find the absolute maximum and minimum values for each function on the indicated interval. So for the first one, we are going to look at negative 3x squared plus 2x minus 5 on the interval negative 1 to 4. I'm not even going to look at this graph. We can figure this out without even looking at the graph. Now, after we get answers, I'm going to switch over to Desmos just to confirm, just to show you that we really did it correct and convince you. But we're going to do this with calculus right now. So we're going to make a list of places we need to check. The definition of being an absolute max or absolute min is that you're either the highest or the lowest. So that is based on your y value. So really, we've just got to check the y values to decide if they're the max or the min. And the places we need to check, well, we were told as long as we're working on a closed interval, those maxes or mins are going to occur at the end points of the interval or at critical values. So I'm going to start a list of places I need to check. I need to check the end points of my interval. I also need to check critical values. So critical values are places where your derivative is either equal to 0 or undefined. So let's find our derivative. F of x is negative 3x squared plus 2x minus 5. F prime is going to be negative 6x plus 2. That is a linear equation. It's never going to be undefined, but it could be equal to 0. So we can set it equal to 0 and solve. So negative 6x plus 2 equals 0. That means negative 6x is going to equal negative 2. If we divide over that negative 6, we get x equals a third. Now you should check and make sure that that number is actually in the interval that you're working with. If it's not, just throw it out. If we got back x equals 12, we would just throw it out because all we're concerned with is what's going on between negative 1 and 4. X equals 1/3 is between negative 1 and 4. So we do need to check and see what's going on at 1/3. That is a critical value. And to figure out who is the maximum and who is the minimum, we need to see which one is the highest and which one's the lowest. And the y value will tell us that. So we need to figure out what f of negative 1 is, what f of 4 is, and what f of 1/3 is. We're going to take these x values and plug them back into our function. So I've gone ahead and I have filled in our functional values for f of x at negative 1, 4, and 1/3. And now all we need to do is compare those y values to figure out who's the max and who's the min. Whichever y value came out the largest is our absolute max. And negative 14/3 is about negative 4.67. It's negative 4 2/3. That might be easier to compare. So whichever one of those y values is the largest is our absolute max. And that is this one. If we were to compare where each of these was located on the graph, this one would be the highest. Negative 10 and negative 45 are both lower. So this is our absolute max. And it's actually the y value that is the absolute max. So we would say we have an absolute max of negative 14/3, and it is located at x equals 1/3. X is just the location. It's the y value that decides if it's the max or the min, because the y value is what tells us how high and how low. And then our absolute min is the smallest y value, the lowest y value, and that's definitely this negative 45. That is by far the lowest point on the graph, if those are the only three we get to compare. So then we would say we have an absolute min of negative 45. And it occurs at x equals 4. So I'm just tracing it back over here to see where it happened. So the x has nothing to do with how high or how low. Remember, the x-axis is the horizontal axis. The y is what tells us how high and how low. So the y is what dictates whether or not we have a max or a min. So it's the actual y value that is the max or the min. X is just the location, left or right, from the origin.